So my name is Cammy Peterson. I've been faculty here at BYU since 2016 in the ECE department. Today, what I want to talk about is cooperative control algorithms for autonomous systems. This is research done, of course, with a lot of graduate students. And I'm part of the BYU Magic Lab with many other professors here as well. So let me pop in here. So jumping in, I thought I'd talk a little bit about UAV technology. So UAV standing for Unmanned Aerial Vehicles technology. So sometimes we call these drones as they get used. And it's been pretty amazing over the past decade or so, just the huge jumps in innovation and technology that has come out around this. So I thought I'd share some of the directions that I think are really interesting, and maybe you've seen some of these as well. But up on the top left, hopefully you can see my pointer, we've got a Mavic Air drone, and these are really DJI makes these. They're as well as many others. But kind of the cool thing about it is you can throw them up in the air. You can say, "Hey, follow me," and as you're skiing or hiking or mountain biking or whatever, you've got a drone up there that can take pictures of you and get really good video. Flying with these are amazing because they've put a lot of work into the stabilization and the automation of it. So you can send it to waypoints, you can use joystick controls, and it's really smooth and really easy to control. Whereas, a decade or so ago, like flying a drone like this, you kind of have to have a lot of experience in being able to get it up. But these are very easy to get up to speed quickly, and really kind of fun toys for recreational use, for videography, that sort of thing. Another example here in the middle, this is kind of on the negative side of how drones are being used. But in the war in Ukraine, drones have become kind of a game changer in terms of what it's enabled, specifically Ukraine, although Russia is also using drones in the war as well. But the Ukrainians are actually taking just kind of commercial, off-the-shelf, really cheap drones, using sometimes duct tape, retrofitting them with explosives so that they can use it as another tool as they're trying to fight in the war there. Another example here, medical delivery with zipline. So we've heard about Amazon that wants to do package delivery, Walmart, a few of these big companies want to do that. In fact, UPS is doing this as well. And Zipline has taken this. They started out of country and are here now. They've got some drones here in Utah even that are sending, doing delivery with like prescriptions, kind of with the healthcare system. They're connecting people there and just making it really easy, really fast to get things that might be time critical. So another way that it's changing our lives, and I expect that to continue on into the future. This example here, this RoboFly, is kind of fun. That's what you see right over there is actually a dime. So this is a tiny fruit fly size drone that the ARL, Army Research Lab, is trying to get together. Is just kind of a really small, extremely small sensor. I don't know that they've gotten anything that's in working order. This is a very challenging problem, obviously, but taking things in a different direction there with miniaturization and the abilities of things that way. Kind of on the other scale of things is these HAIL drones, high altitude, long endurance drones. This is another problem that's really technically challenging, and a lot of big companies have worked on this and haven't made breakthroughs. AeroVironment is continuing to work on this, and hopefully we'll get there sometime in the future. But this is a drone that can fly really high. You see on the top tons of solar panels, so it's trying to like regenerate energy so it can stay up. The goal is for like months at a time eventually, and you can imagine if you can keep something up for months at a time, it can become a substitute to like a satellite. So over maybe a third world country that doesn't have really good infrastructure, this can become cell communication for them or internet for them if you can keep it up in a way that's sustainable. So another challenge, haven't quite gotten there with a couple of these, but it has a high potential to be really impactful. So I like that application. In the center here with this whisk arrow, this is Boeing's prototype for an autonomous air taxi. So a lot of companies are looking at providing air taxis as a way to alleviate congestion or get people from important hubs fairly quickly. Boeing is going straight to just hoping to get something autonomous off the ground. And this vehicle is really kind of fun and very interesting because it lands like a helicopter or quadrotor, where it can land on just a helipad with the props turned up in the air. But then once it gets up, those transition to be forward facing. So then it flies like a fixed wing aircraft. So it's got, by doing that, it's got pretty long range, 90 miles on this one, can travel up to 140 miles per hour. I believe this one is all electric. So it's got that kind of going for it too. So something that they're hoping within, I think the hope is that within the decade, they'll have something like this up and running. So it'd be something to keep your eyes out for and see if that comes to fruition. And another direction where I see things going is kind of in the interface between domains. So between, something that can float and be on the surface and then take off into the air. In this case, this M4 comes from Caltech that they developed, and it's a ground vehicle that turns into an air vehicle. So you've got the wheels, you can see, are actually motors and props, and it can roll along like a car, but then it can turn the props, and so it can take off and fly like a quadcopter as well, and even has some in-between stages where they can make it so it can kind of walk in a way as well. So creating that boundary or going between those traditional boundaries is a direction that you see quite a few of these going. And again, this is just a sampling. There's a lot of other really cool innovations that have happened in this domain. But the great thing is that innovation at this level, at the vehicle level, allows us to do more together. And specifically, what I'm interested in is getting a bunch of these vehicles to cooperate and to work together to achieve some sort of objective or tasking that it's assigned. So that takes us to multi-agent systems. Here's an example. Maybe here's an example of this. Let's look and see. Let me pull this up. I've had problems in the past where for some reason videos stop playing. So I think something about having a connection over Zoom is killing my videos that I haven't quite figured out what is going on. So here we've got the video. Hold this over here so you can see it. So what we've got right here is it's a flock of starlings flying around. And with this flock, you have a hawk that's coming in. So each starling you can think of as its own system. So this is a biological system, but the hawk is coming in and it's trying to swoop in and get all these, capture a starling as it is the predator. And what you see is that as a group, these starlings are kind of morphing around and they're changing behavior. And the interesting thing that we see with this is that there is no centralized leader. There's nothing saying, okay, now you should move like this, another should move like this. It's just kind of organically happening, where it's the starlings that know a little bit about their neighbors. They can see and sense what others are doing, and it reacts to that. So that's something that we call being decentralized, where with a lot of our applications, you may not have a connection back to like a ground station or a computer that can make the decisions of where everybody should go, where all these vehicles should move or behave or act. But they have to make the decisions on them by themselves. So this autonomous piece of things together. And that is where we're kind of headed with this. So what I'm hoping to show today is, or what I will be showing today, are some applications of this. So multi-agent systems, cooperation within that is a huge field. And I want to show just kind of some specific examples within that. But I guess before that, I guess the question would naturally arise as to why we care about this. And I've got up here a couple applications that lend us to examples of when cooperative control, when kind of getting these multi-agent systems to work together is really beneficial. And so up here we see the medical delivery from Rwanda. So you can think of this was Zipline back in Rwanda when they first started off, but that's a country that doesn't have a lot of good road infrastructure. So getting vehicles to go from one place to another, or getting medical deliveries from one place to another on the roads took a very long time. But being able to do it by drone and coordinating, scheduling, tasking, when the drones should take off, where they should land, and getting them to cooperate and work together, enable them to get these deliveries in a more timely manner. Another application of this is search and rescue. You can think of if you have multiple drones up in the air searching out a wide region looking for somebody, that you could do that a lot faster and be able to get the help that the people need in a more timely manner. Environmental sampling is another one where this is very important to get cooperation, because with processes like this over large areas, they can be changing in time. So if you were to just have one vehicle, and this is a vehicle that actually can fly through hurricanes, if you have one vehicle in their sampling, that's great. That gives you some information, but it doesn't give you kind of a global picture of what's happening in time sequence. So getting many out there together gives you a very better estimate. And once you have that, you can do things like developing better models of hurricanes or storms, so that you can better predict how they're going to behave. And that's useful for notifying people and helping them avoid dangerous situations. Another application here is something called the loyal wingman. So this is something that the Air Force is working on right now, which is to say that you have a pilot, fighter pilot, and maybe the wingman for the fighter pilot is actually an autonomous system that behaves. So the commander in the cockpit in his vehicle, he's doing his maneuvers and needs support or backup with its wingmen, and being able to do that autonomously is really beneficial for them. So a lot of benefits for cooperative control. These are just some of them. You get increased guarantees of success if some of the vehicles are shot down or have problems and are no longer able to perform. You still have other vehicles that can give you the information that you're trying to get. So this is really a quantity over quality type of situation that gets you faster results. There's also a cost asymmetry associated with this. An example of that, if you're thinking of cost asymmetry, is let's say you're trying to defend an area, and you might have really good surface-to-air missiles that are going to take out anybody that tries to come your way. Well, if the enemy is able to send really low cost, but a lot of vehicles in at you at once, you might have to shoot them all down, and shooting down drones or something coming at you with a surface-to-air missile can be really costly. And so that creates problems where you might be spending $1 million to shoot down a drone that costs thousands of dollars. And so this is a game that gets played in terms of cost to information kind of benefits, rewards. Also, this improves sensing performance. So if you've got a lot of vehicles, you can expand the areas that you can see. You can get updates more regularly. Even looking at the same thing from different angles gives you more information, and that can be better to have low cost sensors looking from different angles than to have just one like really high cost or high fidelity sensor in many cases. And it also accelerates the response speed. So if you've got vehicles that are behaving autonomously, then they can act and just move much more quickly without having to kind of get commands or get support from some sort of ground station. So an example of this swarm, though this isn't autonomous, kind of a iconic one is with Iran. They're very famous for having these speedboats that are really fast and maneuverable, and they do go out and do formations. And it's been a few years now, but they can sometimes go out and harass our naval ships. And you can think one big naval ship, it would have a hard time, or it does have a hard time in that sort of scenario, because there's so many targets moving about, and being able to defend itself against that, even though the speedboats are very low cost in comparison with the Navy ships that go through the Persian Gulf. Okay, so next couple of slides, like I said, I want to show you a few examples, some applications of what's going on, and hopefully the videos will work. But we'll go through talking about conflict detection and resolution, so a surveillance example, some path planning, and then cooperative target encirclement example. And in the last one, we're just going to do this at a very high level to give you an idea of what this is. But in the last one, I want to go into actually some of the details, some of the math of how we come up with these algorithms and how they behave. Okay, so conflict detection and resolution. So this is a project that we're working on. You can see with a couple of students and with a company called 40 Avionics. And what we're doing here is we're doing, there's a lot of algorithms out there that do collision avoidance, and in many cases, they're reactive collision avoidance. So if you see something ahead of you, then you know you've got to turn and maneuver really quickly to avoid running into them. This is more at the level of path planning or trajectory planning of these paths. So knowing that, hey, this is where I want to go, this is the maneuver I want to do, versus other vehicles, you might know what theirs are. So looking at this graph on the right-hand side, like the orange and the gray are two different vehicles, and those are the paths that they want to go. And what's unique about our approach here is that we're doing it in a way that is time-based. So not only do I want to follow this path, but I want to be along the path at certain instances in time. So I want to start at this time, I want to end at this time. And keeping to that time schedule is important in this scenario. So what we've got, so what we developed are algorithms that can find through time when there are going to be conflicts between these two vehicles, and then they can automatically correct for that and find new paths that will avoid coming too close to another vehicle that might be in the airspace. And you see those resolutions or the new paths that get formed with these blue trajectories here. So that is the goal. And looks like these movies hopefully are playing. There we go. So on the left-hand side, what we see is a path planning where we've got a huge obstacle that's going to be coming through. On the right is a whole bunch of vehicles kind of coming at each other and realizing they're going to conflict in the middle, so they've got to come up with these other paths to maneuver around in that way. And on the left-hand side, we've got it so that the endpoints, they're going to hit their time destinations as we want. So it will start at a certain time, it'll get to the endpoint, even though it's got to kind of change its trajectory to get around that obstacle that's falling through the field of view. And we've been able to do this so that it's dynamically feasible trajectories for things like quadcopters and fixed wing UAVs. So kind of an important thing, if you've got a lot of vehicles up flying at once, you need to be able to ensure that you're not going to collide with each other and be able to adjust your paths when needed. Okay, second application. This is one where we did persistence. ISR stands for Intelligence, Surveillance, and Reconnaissance. This was developed in coordination with the Air Force Research Lab. And what we're doing here is we assume that there are specific places, specific locations where we need to go and get intelligence. So you can think that, you know, maybe these 5 different cities have bad guys that we're trying to track, and we need to go and kind of look and see if we can find them. So there's definitive places that we want to go. And this is almost like a traveling salesman problem where you have, you know, traveling salesman problem says you have different cities and what is the optimal path to get through all these cities that I need to go to. And that's a really hard problem, but there's been a lot of research done on that makes has helped come up with algorithms that are computationally efficient in order to do that. So this is close to that, but it's different because we assume that the places we're trying to see have weights associated with it. So we might know that one location or one city might have really high likelihood that it's got the bad guys that we're trying to find there. So we give it a really high weighting to ensure that that it gets viewed, it gets visited frequently. And that means that, you know, maybe the other locations don't get visited before this place gets revisited. So so you can have trajectories that are going back to different waypoints in out of order before it sees the other ones. When we do this, we need it to be decentralized because we're assuming that you can't talk back to a centralized ground station, or that communication might be intermittent. So you've got no guarantees of that per se. The way that we approached this was using something called the Monte Carlo tree search. This is actually the same or a piece of the algorithm or approach that got incorporated into the AlphaGo algorithm. And that's the first computer that was able to beat a human at playing the game Go. So a really complicated game. And it was able to use what we've used this approach in order to come up with good moves of what the computer should do in the game of Go. And we're using this in terms of paths or locations, policies that we should be able to visit. So this, what it gives us is it's a tree search method. So you can go down different options of paths, and it does a really good job of balancing, exploring really vastly different options versus saying, hey, this path gives me a really good high reward, so I want to explore things close to that. So that this exploration versus exploitation balance is kind of built in to this Monte Carlo tree search. So that's the kind of technical background of what we're doing. We also do something where we can break up the complexity of trying to plan the paths of lots of vehicles at once. And we have a way of where one vehicle just plans its path, and then it shares that planned path or that policy with all the other vehicles. And then the other vehicles use that information as they are planning their paths. And as it gets these other paths, it might eliminate where it originally was going to go, but it can then find that vehicle can then find a more optimal path or trajectory that it needs to find. Okay, so example of this. So on the right-hand side, what you see are, you know, there's 5 just kind of randomly placed targets. They're all equally weighted versus on the left-hand side, these are unequally weighted, and it happens to be that target 3, the pink one in the middle, is very highly weighted in comparison to the others. So on the right, what you see is kind of what you would expect. So you've got 2 vehicles traveling between these waypoint locations, And what they just kind of naturally do with this Monte Carlo tree search is they divide up the space where Vehicle 2, UAV 2, is taking 3 of those targets. Vehicle 1 is taking the other 2, and they just keep revisiting them as quickly as they can. In comparison, these weighted targets, what it does, and this is just using this tree search method, is it finds this optimal policy where the vehicles are always going back to target 3, because the weighting on that is so much higher than the others that it wants to be revisited as much as possible. And so it finds this balance between the 2 UAVs so that there's always somebody going back towards it, or it's always kind of the next step that it goes. And it turns out, though this wasn't planned in for this case, what it finds using this Monte Carlo tree search is the optimal path. You can't do any better than what it develops, just kind of what naturally falls out of this tree search method. Okay, so this is the third example in terms of cooperative control and approaches that we've used. And this is something called informative path planning. So the goal of this is really to use information that you know about your environment to find better paths or better trajectories for the UAVs to follow as they're kind of working in cooperation. So it's this dual thing, like you need to know about the environment, so they're sensing as they go, and they're trying to come up with this global map of what's going on within the region that they're operating in. And they're trying to do other things, get other information along the way. So example of what we do with this, we model both adversarial and environmental uncertainties. So you can think that, if there's a radar system or something that could shoot you down, you need to know about that so that you can plan paths around that. But you've got to be able to detect where it is and understand what its range is, what its uncertainties are associated with that. Also, environmentally, you could have a storm or really high winds that would, if you knew that, you would maybe want to plan around that area so you don't get blown off course or have to use a lot of energy to get where you're trying to go. And so using that environmental information informs the path planning. And as we're moving and doing the path planning, we're also estimating the environment. So this kind of codependent situation here. So there's an example of that. The bright yellow represents a lot of uncertainty about the environment. As you get measurements and you understand information, then that gets better and it goes to the darker colors. And so what we have here is we've got 2 different vehicles, again, traveling to set waypoints that we know that they need to visit, but we give them a little bit of leeway in terms of saying, okay, we want you to go here, but you don't have to go directly there. So if you don't go directly there, what information could you learn by moving around? And you can see that when they do that, and they're replanning constantly, so these paths change, but they decide to do things like kind of bump out in their path so that they can gather information as they go and try to reduce the uncertainty in the environment as much as they can as they're traveling through. Another example of where this is useful is something called level set estimation. So this is something where instead of trying to kind of understand exact values in the environment, maybe you just need to know this is a dangerous region, this is a safe region. So think if there was a chemical spill or something with a radiation leak, then you need to know where the dangerous areas are, where concentrations are too high versus what areas would be safe. And so what the planners are doing here is it's trying to categorize the whole environment in terms of these areas. And so it's sampling as it goes. And we have 3 UAVs here traveling. The lighter paths are predicted versus where they've actually been. And what you see is the vehicles constantly replanning. And eventually what they do is they are attracted to these white regions, which are the regions in between the high and low areas. And as they want to go there because they want to figure out, okay, where is this boundary? And they've got to take a lot more samples there. in order to understand that. But in the end, it does a really good job of figuring out which regions are safe versus not, and reducing the uncertainty as much as they can in the whole map. Okay, so finally, this is fourth example. This is the one I said we're going to go a little bit deep, a little bit technical on. But this is coordinated encirclement of moving targets, and with the caveat that we're using only relative measurements. So you could think target tracking is a kind of an easy way to think about this, that you're trying to follow a target that's moving in the environment, like something in a tank or a car. But this might be a situation where you don't have something like GPS. So with GPS, it can tell you exactly where you are in the world very precisely, but there are a lot of situations where that's not available. It could be because of where you are, you get poor reception, or it's kind of a military application, then GPS might be jammed. And so, or if you're underwater, obviously there's going to be no GPS there. And so being able to do this, to encircle the target without inertial position information, is the goal of this here. And what we're doing instead of that is we're taking measurements along, assuming that you can use a camera or some other sensor to say, hey, I know that the target is over at this angle from me, and I know the distance to that target. And that's the information that we use when we're doing this. And the way that we go about this is using something called the Opanoff's theorem. So this is kind of a very core theorem, very fundamental to any control theory for both nonlinear and linear systems, but most especially for nonlinear systems, which is what we've got. And so go through this. I know this is kind of high level, but I'm hoping that we can get at least down to like kind of the flavor or the understanding of how we use something like this in control applications and cooperative control applications. So here we're assuming that we can model our system with some set of dynamics. So some ordinary differential equation as a non-linear function. And you could get this using like Newton's method or some other method to just find out, okay, what are the equations of motion? How is the system going to behave? And if we've got that, and then we've got an equilibrium point, which we're going to kind of set to be at the origin within a region, then we need to come up with a function d that maps from the domain to our real number space. And this v has to be a continuously differentiable function such that the following criteria exist. So there's 4 criteria that we've got to go through. The first is that at the equilibrium point, the function v has got to be equal to 0. The second is that this function has got to be positive definite, and we're going to say that it goes to infinity as we're going outward to infinity. So this, what we've got here is a perfect example of this, something that's bowl-shaped. It goes to 0 at the origin, but as you go further away, it gets higher and higher in terms of value. And so you can think of, the x and the y there. That would be our direction in this 2D system. And then the theorem says that if the derivative of that function, which is a function of our equations of motion, if that is less than 0, then the origin, our equilibrium point, is going to be globally asymptotically stable. Meaning that if these conditions hold, then we can guarantee that our system is going to go to the equilibrium point as we need it to do. So it gives us a guarantee of stability as opposed to hoping that we throw in a control algorithm and it just flies off or does something unexpected. So this is very important in terms of providing guarantees, providing safety, ensuring that it's going to do what we want it to do. Now, intuitively, we can think about this pretty easily. So if you think of let's say a pendulum, and if there's friction at the point of the pendulum, so the pendulum we know will swing, but if there's friction, it's going to slow down and eventually end up just going, being aligned straight down. And this is what the Lyapunov's theorem is saying. So if we think of maybe our function V as the energy of the system, and then we look at the derivative of V, so how is the energy changing as the pendulum follows its trajectory? So as the position of the pendulum is changing, if that's less than 0, then we're saying we're losing energy as it goes along. So if you're losing energy, then eventually it's going to tunnel it down to that equilibrium point until we're at the lowest energy state that we can get to. So generally, this is kind of what we're saying, and we just need to be able to formulate this idea in terms of UAV and the system that we're trying to do, which is in this case, encircle a moving target. Okay, so this is the setup. So we've got our UAV, we've got our drone. It measures the angle to the target. So in this scenario, we're trying to encircle a boat that kind of represents poachers that are fishing in an area that they shouldn't be fishing in. So trying to stay around that. We've got that angle, we've got the distance to the target. So with those two things, we can measure our relative information to the target. We're assuming that the UAVs travel at a set speed, so we're not doing speed control where they can speed up or slow down. And we also assume that it's got pretty simple dynamics, that we're just, what we control is we can control the direction that it's pointed, so the rate at which it turns. And given that, let's use the Lyapunov's theorem in order to show how this works. So the first thing that we need to do is write out the dynamics, and I'm not going to go through that, but we can pretty easily, with a simple model, write out how these values that we're working on can change. And importantly, the angle between the target changes as a function of how you change the direction of the UAV. So this is what we can control, is this U, and it falls into these dynamics here. The next thing that we need to do is we need to find a function V, a potential function, to use against this. And what we chose for this one was to look at the difference between the desired circle center, so where you want to encircle with the target, versus where you actually are at that any given point in time. And we can do that. And these are the dynamics for assuming actually that you're stationary, the target. And if you take the derivative of V, given that function, you get this. And the cool thing about this, so this we need to ensure is less than 0. And we don't know what that is because, B is going to be positive, but alpha can be anything. It can be, target can be behind you, it can be in front of you. This value here is just the parameter of how quickly you want to go around the circle. But the great thing is, this is what I can control. This is the value that I can change. And if I want V dot to be less than 0, then I can pick this value to make sure that that happens. So we choose that, and choosing this U value here with a gain K that's just some positive number, then you can see if I plug this U in here, what's going to happen is that's going to cancel out with this. That 1 is going to cancel out. And what you're left with V dot is a positive gain value, a distance that's squared, and a cosine of an angle that's squared. So that, because those terms are squared, those are guaranteed to be positive. You've got a negative sign out here. So V dot is going to be less than or equal to 0. And so this guarantees the Lyapunov's theorem that things are going to converge to our origin. And we chose our origin to be the difference between our desired circle center and our actual circle center. So that guarantees that it's going to converge to a circular formation. We've got 2 UAVs. Again, this is the stationary case that are traveling around here. And it's a little bit slow to converge because we intentionally picked a K value that was not really high up there. And in some of the later simulations, we turn that up so you can see that things can converge a lot faster and see the difference that that makes. But what you see happening here is we had a target that started within the desired circle center, one that started without, and they both converge to the actual circle center. And once it gets there, it's guaranteed using the Lyapunov's theorem to stay there, which is Really cool. So guaranteed, you've got theoretical constraints around the performance of what we're going to do. So now we want to do that for accelerating targets. This throws a little bit of a wrinkle more in the math. It's going to change the dynamics of the target, not of the vehicle, but of the target. And the idea of what it means to encircle it is even a little bit tricky, because if you've got, in this case, a constantly moving target throughout here, you're going to have this trochoidal path, and the vehicle path itself is going to be moving, but if you look in the fixed frame, this means it will be directly over the target as it's moving. So a little bit trickier, and that comes to play in the math. So this is really ugly, but as you take v dot of this equation, now with a different error, because you can't just say circle centers, because that definition, the circle center is constantly moving, but we're taking the error between what our desired angle we want to be is, and the actual angle that we're at, as well as the desired distance away from the target versus the actual distance away from the target. If you do that, plug it into this V, then you've got something that really looks like a mess. But we can still do the same process that we did before, because we've got this U value here, and we can pretty much cancel out anything that we need to and choose a U such that we can guarantee that V dot is going to be less than 0. So this U, again, really ugly math, but it'll do it. It'll cancel out a lot of these terms, and what you're left with then is two gains now. So two gains that are guaranteed, that you choose to be greater than 0, and a bunch of squared terms. So those are all going to be positive. You've got a negative in front of it. So this V dot is guaranteed to be less than or equal to 0. And you could take this control algorithm, and you could kind of pick it apart and say, okay, intuitively, what's going on physically as we're trying to converge to these vehicles? And we did this for a paper that we wrote, and we're able to kind of pick it apart and realize what was going on in very specific cases, but it's really ugly and really hard. And kind of the cool thing about this approach, so there's, many control algorithms, something like a proportional controller will just do something that's intuitive in terms of saying, hey, I'm off, my error is this much, and I need to correct and go closer. And it will do that proportional to whatever the error is. So that's really intuitive in terms of what's going on. This is not so much, but that's kind of the cool thing about this, is that you can still guarantee that this is going to work, despite not really understanding what the control algorithm is telling the vehicle to do. So example of this is with a constant velocity target. So on the right hand side, you see the frame as though it were moving and always centered over the target, versus on the left where you see it in an inertial frame. And again, what you see is that on the right hand side, this is really easy to see that it gets to the desired circle around the target, and then it stays there. Like once it gets there, it's not going to go off, but whether it starts inside or outside, it's going to be pushed to that desired circle. This is now 5 vehicles with an accelerating target, so we can bring the acceleration into this. And again, it's able to get to that circle center and then stay on there, encircling it with only this relative position information. So that's, again, this is just a sampling of different ways that, or different problems or challenges that we face when we're dealing with multi-agent systems. So conflict detection and resolution, being able to ensure that you're not hitting each other, cooperating when you're trying to gather information from the environment. And we tie that in with the path planning as well, being able to sense and plan paths within the information that you've had. And also this very specific example of needing to encircle targets when you have limited information that you can that you can use in order to create that formation around the target. So yeah, I hope that was interesting in terms of just kind of getting a flavor for the research that we do and for some of the challenges that we hit. And I guess if you have any questions, you can always email me or let me know. Thank you.